Billions of years ago, Mars was a warm, watery world. Today, it hangs in our night sky as a frozen, barren desert. To understand how a planet loses its oceans, we have to look at the center of our solar system. The sun provides the heat and light that enables life, but it also violently ejects extremely powerful streams of charged particles and intense solar flares. Earth survives this constant barrage because our strong magnetic phenol deflects to solar wind. Mars, however, lacks that protective shield. Without it, the sun's radiation physically bombarded the planet, stripping away lighter atmospheric gases like helium and hydrogen over millions of years. As the Martian atmosphere thinned out and disappeared, the surface lost its ability to retain heat and pressure. The sprawling oceans simply boiled off into space, leaving behind a permanently frozen rock. If humanity is going to establish a long-term presence on this desolate world, we first have to prove that the red planet still holds the vital resources the sun tried so hard to erase. In the late 1800s, telescope observations led astronomers like Giovanni Schiaparelli to map intricate geometric lines across the Martian surface. He called them canali, which many interpreted as artificial water channels built by an extraterrestrial civilization. That illusion held until the 1960s, when the Mariner 4 robotic probe completed the first successful flyby. Instead of a vibrant society, its grainy photographs revealed a bleak, heavily cratered, and entirely dry landscape. A decade later, the Viking landers touched down with a highly specific goal hunt for life. They scooped up soil to test for methanogenic microbes. Methanogenic microbes are single-celled organisms that produce methane gas as a byproduct of their metabolism, which serves as a clear chemical signature of life on Earth. The tests came back empty. Scientists quickly realized that the unique chemical makeup of the Martian dirt, combined with relentless solar ultraviolet radiation baking the surface, created an intensely hostile environment for any organic matter. Sitting absolutely still on a dead plain wasn't going to solve the mystery of what happened to Mars's ancient oceans. To truly read the planet's history, we needed to build machines that could move. In 1997, the Pathfinder mission deployed a small, automated vehicle named Sojourner. This tiny rover proved we could successfully drive a robot across millions of miles of empty space to explore an alien landscape. This success paved the way for Spirit and Opportunity. These twin solar-powered rovers were deployed to opposite sides of the planet, acting as fully equipped robotic geologists with a single directive: find physical evidence of ancient water. Spirit landed in a massive crater covered by a layer of ancient lava. After driving several kilometers to reach a nearby mountain range, the rover identified rocks saturated with iron and magnesium. On Earth, this specific chemical signature only occurs in warm, wet environments. On the other side of the globe, Opportunity landed directly inside a small crater and immediately transmitted images of sedimentary, layered rock. On Earth, these specific layered materials only accumulate at the bottom of long-standing liquid oceans or lakes. The rover successfully proved the planet was once soaked in water, but history books don't keep astronauts alive. For a human colony to survive, we need access to water that is still there today. In 2008, the Phoenix lander touched down near the Martian northern polar region. Instead of driving, it was equipped with a specialized robotic arm designed to dig directly into the crust. Just 6 centimeters below the dry red dirt, the lander's scoop scraped against bright white material. It was frozen water. We had finally touched the remnants of the Martian oceans. Identifying accessible ice confirms we have the base ingredients for life, yet the surface environment remains a lethal variable. The planet experiences violent global dust storms that can rapidly choke the sky and completely block out the sun. In 2018, one of these massive, planet-wide dust storms swallowed Mars. It lasted for months, coating the Opportunity rover's solar panels in thick dust and permanently draining its battery, ending a historic 15-year expedition. We now know the water required to sustain a human presence is buried safely under the dirt, while the surface remains a lethal trap. That reality forces a radical shift in exactly how we will build our first off-world home. Mars is an incredibly dangerous place for human biology. The atmospheric pressure is roughly 1% of what we experience at sea level, and without a protective ozone layer, the environment offers zero defense against space weather. The sun's intense radiation comes straight in. Astronauts exposed for extended periods face catastrophic cellular damage and high cancer rates. To survive, colonists cannot rely on surface glass domes. We must bury our habitats deep underground, using the thick rock crust as a physical shield. Digging a safe bunker only solves half the problem. Once shielded from the sun, an underground colony still has to find a way to eat, drink, and power its equipment, completely cut off from Earth's supply lines. The answer lies in a concept called in situ resource utilization. This simply means harvesting and using the local materials found right there on the planet to manufacture whatever you need. Because a round-trip mission to Earth takes a full 2 years, a Martian colony must be entirely self-sufficient. Astronauts will have to mine that subsurface ice for drinking water, extract oxygen from the carbon dioxide atmosphere, and process local minerals to generate their own rocket fuel. As we prepare to extract these resources, we carry a heavy philosophical responsibility. Because we haven't definitively ruled out the existence of microbial life hidden deep underground, we have to proceed cautiously to ensure we don't accidentally contaminate an inhabited world. The data gathered by these robotic missions provides the specific engineering parameters for humanity's next frontier. These machines mapped the resource deposits and atmospheric hazards that determine whether we survive. The moment we step onto the Martian surface, we introduce Earth's microbes and infrastructure to a previously isolated world. It marks the transition from remote observation to active occupation,